physics right now, we are not supposed to lose any information. So that's why we have a paradox. Does not mean that it will stay a paradox forever. Like theory of physics are changing a lot. We are discovering new things. So maybe that in the future, somebody will find a new theory that will explain how uh, this this information is actually not lost, or maybe there will be new theory that are developed that work with the evaporation of black hole. Like, we don't know everything yet in the universe, so it's fine if we have some small paradox or big paradox. It just means that we can continue to study them and continue to do some discoveries.
Yeah, yeah, that's very nice. One quick note, sorry to our YouTube viewers. It took me a bit to start the YouTube stream, so you just missed like the first minute, so it's not a big deal. And we just talked a bit about black holes, and we'll continue talking about black holes. So nothing lost there. So yeah, just for you again, we're here to answer all your questions about astronomy, and you can just ask anything in the chat, and it will appear here, and we can answer your questions. And while we're doing this, we're talking a bit about a few questions from last time. Yeah, sorry for the small delay. Yeah, that was a nice question. That was a bit about the expansion of space. So actually, we got two questions. How can gravity overtake the speed of expansion? The speed of expansion of space. So kind of what happens when space expands faster and faster, and how does it work with the speed of light? And also something about, is space expanding on the molecular level? And this is a really interesting question. So what we know is from kind of looking at the universe from observations, we know that the universe is expanding. And I can show you a little picture here. So we know that the universe from a few thousand years after the Big Bang to today expanded by roughly a factor of 1,000. And actually before that, it expanded a lot more. So the universe started quite small and expanded bigger and bigger. And actually, like, if you can observe this by looking at kind of for example, like supernovae, which have a certain brightness, and you can see at very old supernovae and at more recent ones, and kind of see how far they're away and how far they should be away. And then you can kind of deduce that they are moving away from us. And the first thing I want to say about is kind of the speed of light limit of kind of how fast information can travel. And in theory, yes. So the universe is expanding at 70 kilometers per second for an object that is 1 megaparsec away from us. So if an object is, let's say, 1,000 gigaparsec away from us, it is expanding from us at 70,000 kilometers per second. So really, really fast. And of course, if an object is far enough away, it would be kind of expanding away from us at more than the speed of light. But this is not really a speed it has. It's just kind of space actually expanding. So the object itself isn't moving. And there's no information carried by this, or this distance, on the speed. So that's why the speed of light isn't a limit here. So it can just expand as fast as it wants to. And the question about the molecular scale is actually really interesting, because in theory, yes, space just actually physically expands. So even the space between two molecules would expand. But then the molecules are held together by their attraction, by electromagnetic forces. And these forces would pull those molecules back. So the distance between molecules, let's say in your body or the Earth and the Sun, will not be affected by the expansion of the universe, because the forces themselves keep those objects in a certain distance. So yeah, space is actually expanding on really every scale, but it doesn't mean that every object is going, like, everything is expanding. So a hydrogen molecule will always have the same orbit, and other molecule, everything on like chemistry will have the same sizes. Yeah. We have a few other questions. We had one question about the great attractor and what it could be. Do you want to say something about this, Annabelle?
Yeah, so I don't know if everybody has heard about the Great Attractor, but I did a bit of reading about it, and it seems that it's just a region in space that has a very, very big attraction there. Like, the gravity is huge there, and it's like behind the Milky Way, because like if we look in the sky, you see like the big Milky Way. If you are in a region with not that many lights, you can see in the sky, and actually it's hard to see behind it because it's so bright and very close to us. But if you look not in the visual light, but in different light, you can go through it. And this is a way you can like observe the sky. You can observe the sky not only in visible light, as you can see with your eyes, but you can also observe it in radio, in X-rays, in infrared. It's just like different light energies. So like it's just different way of looking in the sky. So what happened is that people realized that at this place in space, there was like a huge gravity and they could not see what was happening there. So I know that some people think that it might be a black hole, but yes, black holes are very massive and therefore their gravity is huge, but it does not mean that it's a black hole there. It could be other things that are very massive. For example, at the beginning of this Ask an Astronomer question, I talked about clusters. Clusters are just like a lot of galaxies put together. So it's super, super massive. It's actually the biggest objects that are bound by gravity because like you have each galaxy that are attracted together because of their own gravity, and this is why they are put together in a cluster. We can also talk about supercluster, which are just like clusters that have more galaxies than others. So this might be one of the reasons that there is a region in space where there is a very, very big gravity. It might be a supercluster there that create this like effect around it. I don't think we're still sure what is happening there, but I think the main theory right now is that there is a supercluster there.
Yeah, actually, what I also find interesting, like actually that the most mass in clusters, in galaxy clusters, isn't a black hole, and it's also like not the stars, but it's just all the gas is in there. So almost all of the mass of this like beautiful stars and galaxies you see in the sky is actually just the gas that you can't even see with your eyes. So
exactly. Yeah.
Impressive.
Yeah.
Oh, we got a question on YouTube. How? Oh wait, let me actually open it on YouTube. I can't read it on the screen. We'll come to the question in a second. Wait, let me make this a bit bigger. 1 second.
So the question is, how do they even get that kind of data? Is it accurate? What kind of data are we talking about? Like, are we talking about the clusters data?
I guess like kind of. Yeah, right. Do you mean the measurement of the expansion history, or the measurement of what's kind of the size of clusters and the kind of great attractor things? Ah, this data here, this graph on the picture. Okay, I should mention this graph is kind of an artist impression, so to say. So actually the expansion is just much stronger than this, so it doesn't really fit on the paper. But I can show you a way we can find this data. So there are certain things in the universe that we call standard candles, and I actually have a nice illustration for that, which I'm trying to open in a second. Yeah, so what we have is a certain type of supernovae, which is called supernovae 1a. They always happen by a big object, like a big star, like losing mass into a small object like a neutron star. At some point, this neutron star gets so heavy that it can't support its own mass anymore and it collapses into a black hole. And this creates kind of a supernova, and this is always very similar. So we have certain ways of figuring out how bright these supernovae are. So we know if it has this color, it's roughly this brightness. And then what we do is we observe these supernovae in various galaxies, like close to us, further away from us. And from the brightness, we can see how far away the supernova is. And from the so-called redshift, so this kind of gives you, if you look at certain emission lines, let's say the emission line of some molecule transition or so, this always has a certain frequency. And this frequency shifts over time. This is so-called cosmological redshift. So from this redshift that we can measure, we can know how old is a supernova, how long ago did it happen. And then we combine the distance we know and the age and can kind of make a plot of how long something ago it is and how far it is away. And then we get a plot like here on the right side, where we have the distance and the kind of, let's say, age of something. And then you can kind of measure the expansion history. And this only works for kind of relatively recent things. So for older things, we need other observations, and like there are various observations, for example, involving the cosmic microwave backgrounds, and that allows us to kind of piece together our way and to see how the expansion works. So yeah, that's quite impressive. Yeah. So we have a few other questions. Oh, that's a nice one about how we can harness the energy of the sun, and what do you think are the best options for, let's say, humanity in 20,000 years? How will we make our energy? Do we throw stuff into black holes, or do we throw stuff into the sun, or do we just build a sphere of solar panels around the sun?
I don't think we could use something from the black holes to have an effect and be able to move around in space. I think that would be not in our grasp right now, just because black holes are so far away from us. So I don't think we would be able to use black holes to move around in space in the future. Do you have other ideas what we could use, Stefan?
Yeah, I think just putting like a load of solar panels around the sun, like Dyson sphere, is a really promising, like kind of a thing we can do on our solar system, and without like traveling to a black hole, which is really far away. So I think the sun is the only like big energy producing thing that is like close to us. Except of course we could just start our own fusion reactors. I think we can do this in 20,000 years. Yeah, we just got another question on YouTube about how we get these parameters, how we get this to measure the brightness. So there are various things you can observe from a supernovae. So the one thing is you can observe how bright it is as a function of time. So you see the beginning, it's just dark, more or less, like a normal galaxy. And then you see in this galaxy a supernova starts, so it gets really bright. And then it could go like brighter, less bright. I don't know how the exact shape looks like, but you kind of get a certain shape. And then there's a thing called spectroscopy. So if you have a certain kind of telescope, more or less a very precise measurement, you can get kind of what color the supernova is. So you can see all the frequencies of all the radiation that reaches us. And from this you can also kind of see what kind of supernova it is. And what we actually do is we don't really know exactly how this works, but we just look at supernovae that we know are in, let's say, galaxies that we know how far away they are, and we know how bright the supernova should be, given that we measured it, and then we kind of calibrate this dependence. So we look how bright should this be, how bright does it look, what are the kind of parameters, the color, the shape of the signal, and then we do this for a few supernovae, and then we kind of get good at doing this, and then we can do this for a more difficult supernovae, and kind of we don't have to, once we calibrate this formula, we can use this formula to infer how bright the supernova is. There's actually quite a lot of research on this topic, so it's not done yet. And there are a lot of people working on how to get the brightness of a supernova from the measurements. And yeah, that's a way to do it. Can you read the next YouTube questions, Ella? Because I can't see them at the moment, but I'll work on it.
Yeah, I can do that. So we have another question where it's, do all galaxies have black holes in their center? If yes, why? So for now, we think that all galaxies have black holes in their center, except maybe the very small galaxies, just because maybe they are not there yet. But yes, like all the galaxies, we can see there's a black hole in the center. Our problem right now is we are not sure how they're created, those black holes. They are so massive that it would be very difficult to create. So to give you an example, to create stellar mass black holes, so black holes that are about the mass of the sun, what will happen is that when a star is dying, what will happen, as Stefan explained earlier, it will create a supernova. But at the center of that supernova, there is a very compact object that will be created. And depending on the mass of this star, it could create a black hole. So like bigger stars, when they die, they will explode as supernova, and the inside of them will like implode and create that black hole at the center. So very, very dense objects at the center of supernova. But those black holes are not that big. They will be like about 4 to 100 times the mass of the sun. So it's not that big. Well, at the center of galaxies, those black holes are pretty big. They would be like a million to a billion times the size, the mass of the sun. So it's very, very big. It cannot be created by just stars exploding. And also, we don't think the like universe is old enough to have just like those small black holes merging into each other and creating those bigger black hole. We don't think it's that yet. So the theory right now is just that you would have black holes in the galaxies, and when galaxies like merge together, maybe the black holes in the galaxy would merge together and it will create like bigger black hole. And because of just like the black hole moving, it could like go at the center of that galaxy, but it's really not sure yet. So there are still a lot of things to study on that topic to better understand why black holes are that big at the center of galaxy, why there is one at the center of every galaxy. So study is still going, and maybe in the future we'll know more about it.
Yeah. Yeah, actually, we got quite a few questions now on YouTube. So, greetings to Florida. Actually, it would be nice to know like where you're all watching from. So, if you want to comment on from where you're viewing us, that would be really nice. We got a question from Mr. Thomas Anderson about black holes. Is a black hole a round object, or is it a hole with no bottom? Do you want to say something about this?
Yeah. So it actually depends like how you think about it. So if you look at a black hole like more in space, what you would see is more like, it's not just round, it's a sphere, it's in 3 dimensions. It's just that when we see images, it's always like in 2D because that's what we can see in space. But it's actually like around a spherical thing, like you can see in any picture that Stefan is showing right now. But what it actually is, when you are talking about like a hole with no bottom, we could maybe talk a bit about like space-time. So what happened is that our universe, yes, it's a space, it's in 3D, but actually it's more like space and time. So it's in 4D. And how you can imagine that is if you take, for example, like a sheet of like that goes on your bed, it's really soft, but it's pretty flat. But if you put, for example, like a small ball on it, then it will create like a small hole in that sheet, just like a bump. If you put a bigger ball, it will create a bigger bump. And this is actually what is space and time. It's just when you have massive object, it will create a bump into the space and time sheet. And this is like what happened with general relativity. So like if you have like the Earth with the moon is turning around the Earth. It's just because the moon is creating a smaller bump, so it's turning around that bigger hole that is the Earth. But because black holes are so massive, they are like extremely massive, the most massive object that nothing can ever go out of. What happened is it's not a small bump or even a big bump. It's actually a hole that is created in that space-time. We call it like I forgot the name in English, but just like we call it just a very, very big hole.
Yeah. So and when people say like singularity, that's what I mean, basically, I guess.
Yeah, exactly. So it's just like a huge ass hole. So what happened is that nothing can like enter it and then go out of it again because it's a hole without like kind of without bottom. It's just like so huge that you cannot get out of it. So your two definitions were good. Yes, it's a sphere when you look at it in space with like telescope with like images that you can draw, or like even the image that we saw from like the black hole of M87 in April last year. You can see like that sphere at the center. But if you imagine it in like the general relativity theory, then yes, it's a hole in the space-time sheet. I hope it answers the question.
So you have actually you have a three-dimensional space-time with like a hole in it. So you can't really draw this on paper, I guess. So that's why you have to draw it in like
Yeah.
2 dimensions and then make a hole in it. But yeah, that's confusing a lot of people. Like we had quite a few questions on this in the last weeks of like it's always like drawn as a 2D sheet with a hole, but actually it's a 3D sheet with a hole in the fourth dimension, which is really hard to draw. We got a lot of the questions.
Yeah.
What could possibly happen if you enter a black hole? That's a
Okay,
really nice
so
question. Go ahead.
yeah, this is a very interesting question, and I think we get it a lot. Um, it's a question that we can only answer with theory because we don't really know the real answer. Nobody knows actually right now. Um, so there's a few theory. So maybe what happened when you enter a black hole, just nothing. It's like nothing happened to you. You either die or I don't know.
I mean, you will probably
And
die at some point because
yeah, no.
once you're in the black hole, you can't come out. So it's kind of not so
Yeah.
nice.
Another theory, I don't know if you've
Uh,
ever heard about it, but it's called wormhole. So what happened is that you have a black hole and you have like a corridor that we call a wormhole, and at the end of it, it's called a white hole. So it's just like black hole, white hole, and at the center you have a wormhole. So what happened would be that when you enter that black hole, you could go out of the white hole, and that could make you able to move into the universe. Because what this theory is talking about is that maybe what happened is that the space-time sheet that I was talking about is like kind of curved. So you have the black hole, you have your sheet, and you have the white hole here. So by going through the black hole to the white hole, you might be able to move into space and time. So either go in the past, in the future, or a different position in the universe. Another theory is that that white hole would be like in a different universe. But just to make it clear, all those theory are theory. We really don't know what is happening right now.
Disclaimer: please do not try this at home.
Exactly. And it's like it will be hard to see what is actually happening. Right now it's just theory on papers because like nothing goes out of a black hole. Light cannot go out, so we cannot get information out of a black hole. So how can we study something inside if we cannot get anything from the inside? So yeah, right now it's really just theory. It will be hard to say when we'll be able to understand it, if we will at some point. So yeah.
But actually, like what we can say is about what happens before you enter the black hole.
Yeah.
So kind of before you cross the event horizon, we are pretty sure what happens. Afterwards, not so sure. But actually, like, if you're falling into a really small black hole, then you have a problem. Because let's say you're falling, here's a black hole, and you're like the person falling onto the black hole. Your feet are about 2 meters, or let's say 1.80 meters or so, closer to the black hole than your head. Which means if the black hole is kind of small, then the force it's pulling on your feet is much bigger than the force pulling on your head. Which means your body gets kind of pulled along, which is what people actually call spaghettification. Which is what would happen to you quite a long while before you actually reach the edge of a black hole if it's a small black hole. If it's a big black hole though, this is so large, the kind of event horizon, that you can pass the event horizon and you wouldn't even notice. Like you would just notice, okay, my walkie-talkie or my kind of communication device stopped working because my signals can't escape the black hole anymore. But you wouldn't really feel anything special once you kind of cross the event horizon. Eventually, of course, you would get too close to the black hole and probably die. Or maybe some wonders happen and you have like a white hole thing, but yeah, that's kind of speculative. Yeah, we got a question a bit about kind of our PhDs and topics, what motivated us to start to choose this area of our PhD. Yeah, so I can start with this.
Yeah.
I think, like, especially like cosmology has kind of always fascinated me. So actually, I started studying physics. So I didn't do the kind of astronomy degree, but started with physics and now do astronomy. And then like in physics, it was always kind of, okay, understand more what happens, understand the universe in more detail. And there are kind of these two directions of either like, okay, try to understand how every single particle works and all the elementary physics, like quarks and bosons and photons, etc. And the other side of, okay, how does the whole universe work? And like, what's making the universe expand and why is it there? Like, why is there a Big Bang at the beginning? And this is just, I found this really fascinating. And it's just like, I'm really happy that I can study this. This is just like the kind of ultimate question. And yeah, that's kind of, I chose this because it's just so interesting.
Yeah, so me, I don't know, I was always like fascinated by space, like what is happening there. And I remember, I think it was in high school, in like third year of high school, we had to do a presentation on anything, any like question we had. And my question was like, what is a black hole? So like very off topic with everybody else, but like I was already really interested into black holes. Um, so I think I kept that interest in mind. Like it was really just fascinated, and we don't really understand it. And then I continued my studies, and I went into physics like Stefan. So I did my undergraduate in physics, and then I wanted to just continue to understand what is happening around us, which is why I went to physics. Um, and then I kept in mind always that I was interested in space. So that's what brought me to astrophysics. And at my university, there was a professor that was studying black holes in clusters of galaxies. So I was really interested by her topics, and also she was a really great teacher and professor. So I decided to go with her, and that's what brought me in this field, and I'm really happy about it.
Yeah, we got some great more questions coming up. From Fat, we got a question. Does a black hole does a black hole have a range that it starts to absorb things? So, I mean, certainly there must be some way, must be something, because we're not getting absorbed at the moment by the supermassive black hole in the center of our galaxy. Do you want to say something about this?
Yeah, so I can go ahead. Like, black holes are big and they might seem scary, but they won't eat us. Like, we are way too far away from black holes. What happened is that black holes, what will happen is that uh, the matter won't just like fall into it. So as the image I think you see right now in your screen, you have like the black hole at the center, and around it there's like a disk of matter. So what happened actually is that when like matter is a bit too close to a black hole, it will start by like going around the black hole and creating that disk of matter. And because the disk is so like compact together, the particle will like um, lose energy just because they are like going with other like different part of particle will just like go and do this together, and they will lose energy. And it means that the particle will go closer and closer to the black hole until it falls into it. But this disk is not that big. Yes, it's big just because like black holes are also very big. For example, like the biggest black hole would be maybe like the size of the solar system. So if you take our solar system, then this can be the size of a black hole. It's huge. It's actually like the image of the black hole they took is actually that it's the size of our solar system. So they are huge, which means that obviously the disk around them is really, really big, but it's not that big in comparison. I don't have numbers, but it would be like less than like a couple of uh, like light years. And a light year, do you remember what's the how
I,
many kilometer a light year?
I don't remember exactly, but I think like we had like the slide here that you sent me with like the kind of the really big black holes are like a few million kilometers,
Yeah,
or actually like yeah, this kind of really large one that you mentioned is like billions of kilometers, but that's not that big in like astronomical kind of terms.
exactly. So like there's no need to be frightened about like us be falling into a black hole. So like to give you an example, the black hole at the center of our galaxy, yes, it might be seem frightening, but it's actually so far away. So I looked, and it's at 26,000 light year from us, which means it's at 2,250 quadrillion kilometer. So quadrillion is a very high number, so don't be afraid about that. To give you like a scale, the distance between the Earth and the Sun is like 150 million kilometer, which is the equivalent of 8 light minutes. So it's not in minutes now, it's in years, and it's in thousands of years. So it's so far away, like there's no need to be frightened of that black hole.
Yeah. So actually, this kind of ties into our next question that was about what's like, if smaller black holes have like a curved space more than that bigger black holes. And for black holes, there's like kind of a number that's called the Schwarzschild radius, which is kind of, if I show you the picture again, the kind of, you see this kind of disk of the black hole. This is kind of the shadow of the black hole. And it's more or less, not precisely, this Schwarzschild radius. So this is the kind of radius from where nothing can escape anymore. So where the space is really strongly curved. And this radius is proportional to the mass. So if you double the mass, this radius goes up by a factor of 2. Actually, because this is radius, the volume goes up by a factor of a lot more. So actually, bigger black holes are less dense than smaller black holes. Yeah, right. So actually, I mean, kind of, if this kind of the question is, smaller black holes give you kind of much stronger curvature of space on a shorter distance. So because for a black hole is like, let's say, a few kilometers of Schwarzschild radius, within like a few kilometers, you get a huge kind of curvature of space. While for really large black holes, their Schwarzschild radius are huge, like as we just said, millions or billions of kilometers. So the stretching of space is much more gradual, even though it's ultimately heavier and larger. And yeah. And there was a question about how we calculate the bend of space-time in a black hole. And there was an article, I was just reading from the comment, that said smaller black holes, but right, yeah. How would we calculate this? So general relativity gives you a few kind of equations that tell you how how space bends around matter. So there's this thing called the Schwarzschild metric, which was actually a really there was this physicist called Schwarzschild who tried to kind of understand, these Einstein equations look quite interesting, but I can't really make anything of it. So let's just try some really simple solutions. And one thing he came up with, okay, let's just say I have some object with mass and around it everything is spherically symmetric. And this turns out to pretty well describe a black hole. And what he found is that there is this kind of behavior of, there's this kind of curvature of space. It just comes out of the Einstein equations, more or less. So it's not that there's not that much theory needed to compute this. Of course, it gets more complicated if the black hole starts to spin or if the black hole is charged. But we also have math for this, and we can all kind of solve this with general relativity to get those answers. Then we got a thing about what happens when black holes die. Do you want to say something about this, Annabelle?
Which one, sorry?
What happens when black holes die?
All the information. Okay. So yeah, how can black hole die? It would be via like the Hawking evaporation I talked about earlier. If you missed it, it's just simply that Stephen Hawking actually talked about a theory that means that black holes lose a bit of information over their lifetime, and it would mean that that information go into space as evaporation, that we call. So at some point, maybe if the black hole is like isolated, then no new information would go into it. Then
so new matter, essentially.
Exactly. If nothing goes into the black hole, then it means that its mass won't become bigger, so it will only evaporate. So it will lose mass over the time. So at some point, it could disappear. But the information inside the black hole would not totally disappear just because it was evaporated into space. But it brings back the information paradox of how this information is evaporating, and this is like a question we still don't really know how it resolved. But the point is, the information is in the evaporation. That is our guess. And for the question of the lifespan, this is a good question. I'm not sure how long it would take, but it's very, very, very long. So right now, even very small black holes that would be created like at the beginning of the universe, there is not enough time yet for them to evaporate completely. So it takes a lot of time. What we know, well, at least what we think we know about that theory, is that in the end, when the black hole would die, it would create a very, very big gamma ray burst. Um, so that's how we think we will be able to um, see the evaporation of black hole, is by that very big burst of gamma ray. We didn't see any yet that could mean a black hole was evaporated, but we have telescopes in space that are looking at that right now. So if it ever happened, we could see it. Yeah.
Yeah, I actually love this topic of black hole evaporation because that kind of connects kind of relativity and kind of quantum physics, and you need both to explain this. And actually, the cool thing is, so we just discussed before, like if you have a smaller black hole, space is curved more strongly. And this gives you more of this evaporation. So the smaller the black hole is, the more actually it kind of evaporates and the more radiation it sends out. And the shorter its lifetime. So actually, like when you think about, like from stars, we know bigger stars burn faster and live shorter. But actually with black holes, it's the other way around. And if you have really tiny black holes, they could live like really just microseconds or like much less. They could just almost instantly evaporate. This is actually why you do not have to worry at all about black holes being created at the LHC, at the Large Hadron Collider. That's why we like kind of shoot particles together in hope of producing interesting stuff. And if there would be a black hole created from all the energy that we have, even though this black hole would evaporate within like microseconds or something, so there would be like no danger at all. Like it could like evaporate before it can accrete anything. There's kind of, it is super fast. And yeah, this is also kind of the reason why you get this real, like kind of, if you have a big black hole, it gets smaller and smaller, the evaporation gets stronger and stronger, so it gets faster and faster, and speeds up, which is kind of why you get this strong detectable thing at the end. So yes, that's really cool.
Yeah.
Astronomy is in general really cool. I think I'm saying this a lot. Oh, if planet X turns out to be a black hole, that would be a really nice thing. So there's this kind of theory of we are like observing the orbits of the planets in our solar system, and some people have theory that there might be another planet, Planet 9 or Planet X, and that could be responsible for some kind of deviations from what we observe. Although we're not sure, it could be other things, but it could also be a planet. And so there are speculations that this planet could be a primordial black hole. So just for explanation, primordial black holes are black holes that were created kind of shortly after the Big Bang. So not from dying stars, but actually just created from when the universe was created and have been there ever since. And there are some theories that these black holes, for example, could make up for dark matter, although they're pretty limited at the moment. So we are quite sure that black holes are not responsible for all of the dark matter. But I mean, if there would be a black hole, that would be really cool. And yeah, like, did you hear, like, what do you think about Planet X? Would you like a black hole in our solar system?
Well, it would be cool. So I think I heard about like a study recently about like maybe this is a primary black hole. So I know some people are studying it and thinking that it's actually a possibility with like the deviation we see right now. It would be cool. It would mean that a black hole is closer to us and it would be easier to study it. Still, I don't think we should be frightened about it if it's a black hole. It would just be really interesting for science to be able to maybe go and study it in the future.
It would be just so amazing. Like, I mean, no, not even only for science, but maybe we could just like make energy out of it or something. Like, it would be so cool. And also, a planet-sized black hole would be really small. So I don't know the numbers in my head, but I think it's like a few kilometers, maybe a few 100 kilometers or so. I think it's more like a few kilometers or less.
Yeah, no, it's really small because like the size of the sun, the black hole would be 3 kilometers.
Oh, okay. I was way off. Then it's like,
yeah, so like the size, the mass of a planet, I don't know the size because it's not like a proportional, but like it would be very, very, very tiny. So there's no need to worry about it.
Okay, so that's fine. Yeah, but it would be really, really nice. Oh, we got loads of more questions. Can dark matter collapse upon itself and form black holes or any astronomical bodies like planets or stars? That's a really cool question. Yeah. So for you to form stars, actually forming stars is a really hard thing to do, because it took the universe kind of hundreds of millions of years actually to form the first stars. Because if you have a big kind of cloud of gas and this gas is usually hot, at least it was in the case of our universe. This hot gas just doesn't want to collapse into an object because it all the way repels itself, and you have to wait a long time for the gas to cool to actually fall into a star. And then the star ignites and gets hot again. It's kind of ironic. But you have to, like, the main difficulty of making a star is just waiting for the gas that will form the star to cool down so it can actually fall together and make a star. And you would think, okay, dark matter, that should be much easier because dark matter can just like go through itself. It doesn't get like the repellent force that you get from pressure, so it doesn't feel any pressure. But the problem with dark matter is, let's like imagine two kind of big dark matter particles. They fly towards each other. They just fly through each other. So there's no way to kind of stop them in the middle and form actually a black hole. So the particle would just orbit itself, would just fly around and form what we call a halo. So kind of a big, like a huge object that's kind of more or less like kind of medium density, but it wouldn't come anywhere close to forming a black hole, at least if it doesn't have anything that slows it down. Because there's no way for it to lose energy. Like, it's kind of the same problem. There's no way for it to cool. And if there's no interactions, there's no way it can kind of give away energy. So it will always have its kind of momentum and its speed, and it will never kind of fall into a single body. So that's kind of the problem with making black holes out of dark matter.
Okay, so we have, do primordial and other black holes behave in the same way after they are formed? I would say yes. So once you have a black hole, black holes are really simple objects. So they might seem frightening and anything, but they are super simple. We have a theory called no-hair theory, and it's because black holes are so simple that we can describe them by only 3 numbers. So the only thing we need to describe a black hole is its charge, its mass, and its spin. And actually, its charge, we really say that black holes are neutral, so their charge is 0, just because if a black hole positive, for example, would form, it will attract negative things, and it will, in the end, become neutral. So we just say that every black hole right now, it's neutral. And then we have its mass, so like just how massive it is. And finally, we have its spin, so like how much it turns on itself. Like, does it spin on itself fast or slow? This is describing the spin. So it's really just that describe black hole. So then if you have massive black holes or very small black holes, they will behave in the exact same way. Just like create disk around them if they absorb matter, and then the matter will not be able to go out of them. And that's about it.
Yeah. So that's black holes have no hair, so they're all the same. Well, not all the same, but there's not that much differences. What would be the possible predecessor cells of aliens would exist? So I guess you after the same way could they be unknown? So I think the question is kind of about how life in general would be created, kind of what building blocks and of what kind of predecessors. And that's also a really kind of question people have thought about for a long while. The problem is a bit, we only have kind of one example to study, which is kind of on Earth, and all life kind of on Earth started the same way. And for example, we could imagine that life could kind of work with different bases than us, so it could have, it's quite possible that it doesn't have DNA the same way we have. But water is kind of a really nice stuff to make life, like for life, because it's a really good solvent and it has all like loads of nice properties that are really helpful for life. So for example, when we search for life on other planets, we essentially just look for water, or we start by looking for water, because it would be really hard to form life without water. It could be, but we don't have, of course, any examples of how to do that or any concrete ideas. So that's kind of a problem of thinking about how life formed. It could form differently, but probably it would also start with kind of some water-based stuff with like similar things to what we call cells. And there are kind of many steps in how to evolve like intelligent life, like kind of humans. Because you kind of need to start first with like kind of one simple cells. Like, first you just start with a bunch of chemicals, and how do you make like a witty cell, like which is kind of made out of loads of atoms and like loads of structure. How do you get this out of chemicals? And that's like a whole large field of study, which I'm not an expert at all in, so I should say this. But there are kind of multiple steps. So How do you get from not alive at all to kind of the first life molecules? How do you get from single cells to multiple cells? These are all kind of things that have to happen at some point. And then you could get life. And I'm sure that there could be there could be different possibilities for many of those steps. And I'm sure if we ever meet like extraterrestrial life, that would be vastly different and far more different than any of our sci-fi books have imagined. But yeah, we can't say, we don't really know any concrete, we don't have any information on how they could be, I guess.
Yeah, and there's like so many steps that happens for us to develop that the chances that like it happens exactly the same way on a different planet are so small that I think there's a bigger possibility that like a different type of life would evolve on a different planet than exactly the same than us.
Oh yeah, we get lots of new questions, so that's great. Just continue with the questions. If we don't finish today, we'll just continue next time. So we have 10 minutes left. Let's go on. Why time is slow at black? So why does time slow down close to black holes? And more in general, I guess, close to massive bodies.
Yeah, so you can help me on that question, but it's mainly related to the fact that black holes are very, very massive, so their gravity is huge. And then it's using special and general relativity that we know that around huge gravity, then the time would slow down. It's the same if we go super fast, then the time will slow down. I think they did an experiment where they sent like an atomic clock in space.
Oh yeah, that's really
and
cool.
And they kept like an exact same atomic clock on Earth, and when the atomic clock that went into space came back, the time was not the same, and those clocks are super precise, so it cannot be like just because of how they are created. It's just because like it went super fast to go into space and come back. So that really explained it proved kind of the special relativity that explained that. I don't know if you want to say anything.
Yeah, I think like the theory behind this is really, really cool, because essentially almost all of like relativity was not single-handedly, but like there was quite a lot of work before, but Einstein did a lot of kind of thought experiments, and it's really impressive on how far you can get with kind of just thought experiments. So with special relativity, what Einstein found out, or what he predicted, let's say, is that if you move, then time runs slower on you, and this comes from the idea of what people actually measured. Light moves always the same speed, no matter of how fast you're moving. So let's say you're on Earth, you shoot a light ray and you measure its speed. Then you go into a train that goes really fast and shoot a light ray within the train and measure there. And it turns out the light goes the same speed, even though the thing that sends the light was moving like from the train. And the only way that this can work is that time slows down if something moves fast. Or in general, if something moves at all, time runs slower for the object that's moving. And actually, if an astronaut is like going around on the space station really fast, like they actually age slightly less. It's like barely detectable. You need atomic clocks for this, but it does have an effect. And then the next thing is, the next thing Einstein thought is, when I accelerate, so let's say I'm sitting in a fast car and it's going faster and faster, I have this kind of acceleration feeling. But this is the same feeling I have when, let's say, I'm lying on a heavy planet and the planet is pulling me down. And his idea was, let's say these two things are undistinguishable. They are like physically really the same thing. Then you do a lot of math, and he comes up with like kind of these field equations that describe how time and space are related. And these equations have a term that tells you if you are close to a massive object, then time is slower close to that object. It just must be this way for the theory to work out. And this works on Earth. This works even my desk kind of makes me age less, but it's just negligible. And kind of Earth is also massive, and it also makes time go slower on Earth. But it's not that huge of an effect. But actually, so what you just mentioned, the experiment with the atomic clocks, they also did this, for example, bring the atomic clock on a mountain and see how fast time goes on top of the mountain and down in the valley, and they could measure the difference. And the difference is exactly what we also predicted with Einstein's theory. So this is really impressive. And when you have like the ISS, you have those two effects. So the astronauts are further away from Earth, so they're aging faster, but they're also moving really fast, so they're aging slower again. And with a black hole, of course, these effects would be much, much larger than with Earth, because in black hole you're much, much closer to a big amount of mass than you're on Earth. So that's kind of the main effect. Why this is so strong for black holes. Yeah, that's really amazing.
We got a question, what is Einstein-Rosen bridge? So of what I understand, this bridge is the same thing I explained as wormholes. So just what could happen, a theory that could happen when you enter a black hole, that you would go through that path and then end up going into different section in the universe, either in space or time or in a different universe. So it's the same thing I explained earlier.
Okay, I didn't know that. That's cool. Yeah, time dilation or black hole, we just said that one. What means time is relative? Yeah, I think so. This is the kind of idea of if you move like, yeah, like there's no thing as like an absolute time. Like you can't say now it's like 12 o'clock and like 1 hour later it's 1 o'clock, because this depends on how you're moving. So if you're on Earth and have a clock, like, I mean, on Earth it works because, well, firstly, it doesn't really matter in real life because the oscillations are really small. And secondly, on Earth, the gravity is small anyway, so we don't notice things, and everybody's on the Earth. But let's say you're like in a society and you're living like all over the galaxy, and some people are living close to black holes, or like other weird things. For example, you can't even say that two events are at the same time. So let's say I have like two light bulbs here, and I turn the two light bulbs on at the same time. Like I turn them on at the same time. Someone who would be taking a train racing past me, if the train would be kind of, let's say, half the speed of light or so, they would see that those times are different from each other. So even saying things at the same time isn't actually a thing you can do in a world with relativity. So that's kind of the idea of time is relative. Welcome, we got one question from Periscope. Let's also answer the one from there. Why is Sagittarius a star called a star?
Yeah, so I know. So why it's that? It's really just like how astronomer like name their stuff. So the star in the Sagittarius A star is like the symbol star and not the name star. And it's because we put that star when it's like the brightest thing in a certain constellation. So I think Sagittarius star was simply, it was like the brightest thing in X-ray, I think. I'm not even sure, but I think it was that. So it's just because it's the brightest thing in the constellation Sagittarius. So it's not because it's a star, it's the symbol star and not a sun, like for example.
Yeah, we got one nice question about gravitational lensing, so let's say a bit about that. So yeah, we talked a bit about how kind of space-time is curved when you have a massive object. So you just imagine what you just said, the kind of the rubber sheet, and you have a bowl on there, like a metal sphere, and this kind of makes a dent in your rubber sphere. So from special relativity tells you that light always moves in a straight line, kind of in this curved space-time. So if you move on a straight line in a curved sheet, then actually this makes you go kind of around. So like light, if you just look close to the surface, it tries to go in a straight line, but because space is curved, it actually gets bent a little bit. And this is what happens in gravitational lensing. So let's say you have a really massive cluster with, I don't know, maybe a black hole in the middle, or maybe not, but just like a huge amount of mass, and preferably also dark matter, great, a huge amount of mass. And then, let's say you have a galaxy in the background, light from the background galaxy can go past this cluster, but then gets kind of deflected from the cluster and can reach us, and can do this from different directions, because it always gets kind of deflected around the big cluster. This is like when you look through a lens, like if you just take a normal optical lens and look through at something, you get kind of this distortion effect. And gravitational lenses work all, like surprisingly similar to like normal physical everyday lenses. And this is kind of the effect we see in this picture. So I think this is a Hubble Space Telescope photograph. And what you see there in the middle, there's a apparently really massive galaxy, like maybe a galaxy cluster. And in the background, there's another galaxy. And the light of this galaxy gets lensed by this cluster. And that's why we kind of see this ring. We see it coming from different directions, but actually it's just coming from one point, but just getting reflected, like around, deflected around this object and lensed into our eyes or our telescopes. And yeah, that's actually a really great effect. Like you can use for lots of things. Like, for example, the oldest galaxies discovered, I think, are from gravitational lenses. So actually, we didn't find, because if you have a gravitational lens, it's like a real lens. It makes the stuff brighter that you see. So you can actually use it to see further in the past than you could actually see, and that's how you kind of find the oldest or the dimmest things in the universe. And you can use it to kind of find dark matter. There's a really famous example called the Ballard cluster, which I think we maybe shouldn't start with now. But that's a thing where you use the gravitational lensing to find actually where matter is, and then you can kind of really find all the matter, so including dark matter, which is a thing you usually can't do really well. Yeah, we got a few more questions. So, do you want to say something about like we got something about wormholes?
I can just say quickly, like somebody said, can the fabric of space-time only be bent or can it be punctured too? I would say that it can only be bent. So it can be bent so much that it looks like a hole, but it won't be punctured. Like it's not like there's a small hole in it. It will be like bent so much that it create kind of a huge like tunnel. But it's not like just like, I don't know, puncture and a small hole is created. Yeah.
And we got one question about kind of the end of the universe, or the kind of, is there some kind of barrier? As far as we know, so there's this thing what we say the observable universe, or some people just say the universe, which is, I don't like this kind of saying, because we don't know if the universe has an end. We don't know how big the universe is. Probably, my guess would be it's just infinitely large. I mean, why wouldn't it be? And there is like no end at all. But there could be, we don't know. So that's kind of the maximum distance we can see. So I think a few hundreds of billions of light years. I'm not sure about the exact number. So kind of from now all the way to the Big Bang, essentially looking at the cosmic microwave background, that's kind of the furthest thing away we can see. And because of the finite speed of light, so light can't travel faster than a certain speed, 300,000 kilometers per second. And the universe is only 13.8 billion years old. There's only so much of the universe we can see, and we can't see behind that. But as far as we know, there's nothing special after the boundary. It's just we can't see further. So the universe will probably just go on. There are theories that the universe could be curved, so that the universe could be actually kind of a closed sphere. And if you go far enough in one direction, you could end up on the other side. But we're not sure about this yet. So it could also be flat. At the moment, our theories are compatible. So both could be the case. Oh, we got something about quantum entanglement. Although I'm not sure. Okay, let's just give a brief overview of quantum entanglement before we stop with today's stream and continue next time. So, quantum entanglement. There are certain processes in physics that produce particles in a certain relation. So, let's say, for example, an electron and a positron. So an anti-electron and a normal electron hit each other, they annihilate into energy. And usually they create two photons that fly away from each other. And there's those two photons must always have, I think, the same or the opposite polarization. So a certain property of those must be, has a relation. But a priori it could be like, they could have a random orientation, but just that the other photon always needs to have the kind of matching one. And until we measure the kind of actual polarization of this photon, it's not determined. So it could be anything. And the kind of entanglement thing is now, as soon as we measure the polarization of the one photon, and the other photon's polarization is determined at the same time as well. And this could happen no matter how far away they are. So what researchers, for example, did in like kind of elementary particle physics, I don't know what kind of researchers were working on this. But there was some...
It's like computer, quantum computer
Oh,
that worked a lot on that.
Oh yeah, that's also a lot of people working on this. Yeah. Anyway, what I did is send the so take this kind of two particles that were entangled, send one to another lab like a few, I don't know, 100 meters away, and then do this kind of experiment. They could still see, okay, we measure this here, and the other particle kind of changes. So that's kind of this entanglement idea. Yeah, but I think like we don't have time to like discuss this in a lot of detail, but I'm happy to discuss this next week. And I think we should also stop here because it's already 5 minutes past 8 and we should stick to our schedule. So thanks a lot for everyone who asked questions. Thanks a lot for everybody who viewed on all the platforms. And yeah, we would be looking forward to you if you join us again next week. And thanks a lot, Annabelle, for all the great comments and great explanations.
Yeah, thank you, Stefan, for inviting me. That's really nice.
And yeah, thanks everyone, and see you next week.